All right, you can see my slides, right?
Yes, sir.
Yes, sir.
Okay. So today I will start on this new topic, um, which is choice theory, and derived from that, we'll talk about consumer demand in a more general way. So we were discussing some very general issues, some philosophical issues about markets and their role. That's a long discussion, so I will come back to it later, and we'll talk about some more of it. But we need to get on with you know developing some of the theory and the maths. So I will proceed there. Any quick questions before I start?
So regarding those case examples that we had yesterday,
Yeah.
they're not in the slides. So will you be incorporating that
Yes,
anytime soon?
I will post revised versions of the slides. I need to fix a few things, like the pictures didn't come out right. So I will fix those, and in a day or two, I will upload the new version of those slides. Yeah.
All right. Thank you, sir.
Sir?
Yeah.
So I had a small doubt regarding quotas from the last class.
Okay.
So we have the quantity that is basically fixed at a particular level under the quota.
Right.
My doubt was that which price is the one which ultimately binds, because the difference can't be explained by a tax either, because the prices we get you via the demand and supply curves are different. So that was my confusion.
Uh-huh. Well, it depends on you know um, that's a little open-ended. So if you have a quota, what will be the price? So let me open up my whiteboard. Oh. Okay. So here's price, here's quantity. So here's our demand curve, here's our supply curve. Okay, and suppose the quota, so this is our market clearing quantity, equilibrium quantity, Q star. And let's say the quota imposed is over here. Okay, so one possibility is that the supply curve effectively becomes this, right? It grazes this part, and then once it hits the quota, it becomes vertical. So in this case, the equilibrium price will be P0. Okay, now the main point is that the derivative loss is still this.
Right, sir.
If the price is allowed to go up to P0, then it's the quota squeezes out consumer surplus to this area, and the producer surplus is below the price line and above. So it's this green area, right? Um, Now, another way in which the quota may be implemented is also to sort of fix the price here. Um, in that case, there's this excess demand, and consumers will then probably face a lottery if you don't allow the price system to function. Um, then often other allocation mechanisms come into play. So if along with the quota, the price is also restricted over here, uh, then uh, then consumers, uh, this excess demand has to be allocated by kind of drawing lots and deciding, out of this much demand and a lesser supply, um, uh, which consumers get to buy the good and who are left out, right? The easier way to think about it is, if there's no sort of intervention in prices, then this part of the supply curve becomes vertical and the price goes up to P0.
All right, sir. Got it. Thank you.
But in either case, whichever way you resolve it, the point is that if you add up everybody, all the consumer surplus, producer surplus, everything, this part is still lost, right? That is independent of how the quota is implemented.
All right, sir.
Sir,
Yeah.
sir, I just wanted to ask, when will we tentatively discuss the problem set like that you have given to us?
Yeah.
So when will that be discussed tentatively?
Either this week or next week. Yes. And after the discussion, I will also give you written solutions. So eventually you'll also have, the written solutions with you. We are in a little bit of a, since everything is unusual this year, hopefully everything will fall into place and run smoothly. I was hoping to start the tutorials this week, but I'm still sort of figuring that out. But by next week, everything will be in place, and surely by next week, the first problem set will be discussed.
Okay, sir. Thank you.
Sir.
Yeah.
Hi, sir. This is my first class. Actually, I just got into DSC in the 4th list.
Right.
So this is my first class. So can you please tell me where do I attend where do I get the video recordings of the previous 5 or 4 lectures that have already been done?
That's on the Canvas. You have to register on Canvas, or I have to get you registered on Canvas with your
Yes, sir.
email address. So,
Okay, sir.
I got the first list as a list, so I registered.
Okay.
And
Okay.
thereafter, what's happening so far, I haven't got any second, third lists yet.
Okay, sir.
The administration. So if you write to me individually, I will just, register you and you can log in.
Okay, sir. Can you just tell me your email address so that I can write to you on that?
Okay, so my email address is pghosh@econdse.org.
Okay, sir. Thank you so much.
Sir, I
Yeah.
would like to add just here that we're actually quite a number of people who have joined late.
Right.
For instance, I also joined yesterday only.
Yeah.
So maybe we can make a list and then send you so you can
That will
add.
actually be excellent idea. As usual, you're ahead of me. So if if you guys can coordinate and send me a list, that will be very helpful for me, because that saves me a lot of time.
Yes, sir. Sure.
Yeah. So excellent idea. Why don't you do that? Some people have already written to me, so but if you all consolidate, I'll wait for that.
Yeah, exactly, sir. So we'll wait for a few days so that more people can join, like for 1 or 2 days, and
Well,
then
actually, why don't you do it right away? We can then sort of do more iterations, because some people who are
sure.
waiting, I don't want them to wait any longer.
Sure,
Yes.
sir. Sure, sir.
So we already have a list in the formal group yesterday. There were around 22 people. We
Right.
can send them for once for the
Okay.
time being.
Okay.
Can you please share the list on the Telegram group, because the WhatsApp groups are full and I can't join the WhatsApp
Yeah,
group.
sure. I will do that. Okay.
Thank you so much.
Okay.
So I have a doubt regarding this concept. Can I ask?
Yeah.
So theoretically, even if we say, can the quota be greater than the market equilibrium quantity?
Yes, it can be theoretically greater, but then it won't have any bite, right? If the quota is greater, then the quota, production and consumption won't go up to the quota. So the marketing equilibrium will continue to be the outcome in that case.
Oh, so it won't affect
That's right.
anything.
Right. Similarly, you can have price floors and price ceilings. If the price floor is set below the market equilibrium price, once again, it has no bite at all. Right. The price won't go down to the floor in that case. It'll go to the market equilibrium and remain there.
Okay, sir.
Yeah. All right. So let's come to our next topic, which is choice theory, generally speaking. Um, Okay, so just to give a little conceptual background and history, early on, even as late as Alfred Marshall, who wrote a famous textbook in the beginning of the 20th century, when economists talked about the notion of utility, they had in mind some sort of psychological measure, right? That, okay, if I consume 2 apples or buy a color television, a flat screen, big TV, I get some utils. Yeah. So this was the concept of cardinal utility. So utility was thought of, first of all, as a psychological magnitude, something in our minds, and it's like height or weight. The exact number had significance. That was the thought. Now, that concept is very hokey because unlike height or weight has well-defined measures. If I say somebody is 6 feet tall, everybody understands what it means, and you can verify with a measuring tape whether that is true or not. If I say somebody's weight is 60 kgs, similarly, you can bring out a weighing scale and measure. So these are objective measures. These are verifiable measures. These are unambiguous and tangible measures. But utility in this earlier sense wasn't like that, right? So, uh, so that created some dissatisfaction, and in the 1930s, there was work by economists like John Hicks, and before Hicks, there was an obscure paper written by Eugene Slutsky, an Italian economist, uh, who developed a very new and different approach to try and develop a theory of choice, right? And that is called the ordinal approach. Okay, so they wanted the building blocks of the theory to be something which is well defined, understood, verifiable, measurable. Yeah. Uh, so they said, okay, let's not talk about this cardinal concept of utility. Pretend as if utility is as easily measurable as weight or height. Let's start with something different, which is rankings, the idea of rankings. So if a consumer faces a number of choices, and if we ask the consumer, say the choices are A, B, and C, uh, and if we make a statement like, the consumer prefers A to B and B to C, then it's very well defined, it's well understood, and we can interview the consumer and find out whether it's true or not, whether it's indeed true that A is a favorite, B is a second favorite, and C is last. As it turns out, and as we develop the theory, you'll see that even though we take this alternative approach, the so-called ordinal choice theory, we can, in a certain sense, recover the concept of utility along the way as we develop the theory, right? So we'll bring in the concept of utility, even though we take the ordinal approach. But the main thing is that with Hicks and Slutsky, the theory of choice and the theory of the consumer and the theory of decision making shifted and started with building blocks, which is rankings rather than the concept of utility, right? So this is the ordinal utility theory. Okay, so let's talk in general abstract terms a little bit about binary relations, right? So this is beyond consumer or choice. Binary relations are everywhere. There are all kinds of binary relations. Uh, so for example, all of these, somebody is taller than somebody else, somebody is a friend of somebody, somebody loves somebody, somebody hates somebody. All of these are binary relations, right? It's a phrase which links two elements, maybe two people, two objects. Uh, so if you think in very abstract logical terms, and let's use the symbol R for a binary relation, right? So these are all examples of R, taller than, friend of, etc. So depending on the context, depending on what kind of binary relation we are talking about, it will have, it may or may not have certain properties. Okay, so what kind of properties? Here are some examples. R may or may not have the commutativity property, for example, right? In some cases, the following statement can be made. For any x and y, x r y implies y r x, right? So, for example, classmate of, if I pick two of you, if I say Pramita is a classmate of Palak, right? Then I can also say the reverse statement that Palak is a classmate of Pramita. Yeah. So classmate of satisfies commutativity, but son of or daughter of obviously doesn't, right? So X is a son of Y, it rules out the opposite statement. The opposite statement cannot be true. Similarly, reflexivity, whether X are X. So if I say at least as rich as, so I am at least as rich as myself, but I'm not richer than myself, right? So depend on which binary relation I'm talking about, reflexivity is may be satisfied or may not be satisfied. An important property which will come in, which will be relevant to our discussion is transitivity. Yes. So if you have any three elements, X, Y, Z, is the following statement true? For all X, Y, Z, X, R, Y, and Y, R, Z implies X, R, Z. Is this true or not? Can we make this assumption about some binary relation? So for example, taller than is transitive, right? If Amitabh Bachchan is taller than Salman Khan and Salman Khan is taller than Shah Rukh Khan, those statements are true. It follows that Amitabh Bachchan is taller than Shah Rukh Khan, right? A friend of is not transitive. Every friend of a friend is not your friend necessarily, right? There are people who are 2 degrees removed who you don't know directly. So it again depends on what binary relation we're talking about. Some of them are transitive, some of them not. So when we take this ordinal approach, we sort of introspect, we look into ourselves, we observe others, and we ask the question, okay, if we say that the consumer has a ranking in her mind among the various alternatives she can buy, what kind of properties does this ranking satisfy, right? Can we make some assumptions which would be appealing to most of us? Most of us might think that these assumptions hold for most people most of the time, right? So that's what we are going to do. We are going to lay down some axioms or assumptions about the particular binary relation, which is the consumer's ranking. Now, as we do that, we will look at it critically a little bit, right? I'll try to give you some sense of why these assumptions won't always hold. But having gone through the assumptions, having cast a little bit of a critical light on them, we'll move ahead and then we'll ask the question, what are the implications of these assumptions, right? So let me move to the assumptions. Before that, we need to talk about the space in which we are doing our analysis. We are going to talk about the preference relation. It's a particular binary relation. So the space is the following. say there are n different goods, a finite number of goods, n can be very large, right? And the goods are indexed by I, right? So there's the first good, there's a second good, and there's all the way up to the nth good. So X subscript I is the quantity of good I, okay? And we have a consumption bundle or a consumption basket or a consumption, or mathematically speaking, a vector. That's the bold X. Bold always will mean vector, just a notational clarification. So when we write this bold X, that means we are talking about a vector of quantities, one for each good, right? So it's something of this form, x1, x2, up to xn. The ith entry is the quantity of the ith good. Now, mathematically speaking, if you look at a vector like this, that's like a point in n-dimensional Euclidean space, right? If you have two goods, you can draw two quadrants and you can plot all these consumption bundles of vectors as a point on the two-dimensional graph, right? But we want to develop a general theory, so we are talking of n-dimensional vectors here. So every consumption bundle is a point in n-dimensional Euclidean space. Yeah, the positive part of it, the non-negative orthant of the Euclidean space. Now, this symbol, curly inequality or curly weak inequality, will represent the following sense. If we write x1, x2, here I've put superscripts. So make sure that you don't get confused by the notation. Here, these x's are bold, that means they're vectors, and the superscripts are different from the subscripts. Subscripts represent which good we are talking about. And here, all the x's are scalars, they're single numbers. Here, the x's are vectors, and the superscripts represent different vectors. They're tags for different vectors, right? So x1 is one consumption bundle, x2 is another consumption bundle, and this notation basically means, in plain language, that the consumer prefers x1, or the consumer considers x1 to be at least as good as x2. We can call that weak preference, right? X1 is at least as good as x2 from this consumer's perspective. Of course, this is a subjective ranking, right? A different consumer might write it exactly in reverse, might say, okay, x2 is at least as good as x1. But once we focus on one particular consumer, that's what the meaning of the statement is. So this curly inequality, the at least as good as, or the weak preference relationship, is a binary relation, which describes the consumer's subjective preferences. So what are reasonable assumptions that we can make? What are reasonable properties that we can postulate about this binary relation? Now, before we get to that, let me also say that sometimes you may want to think about slightly different notions of comparison of consumption bundles, right? So we can talk about strict preference and we can talk about indifference. Now, the assumptions will be laid out on the weak preference relationship, on the weak inequality side, right? But we can give definitions of the strict inequality and this sort of indifference thing in the following way. Here's the formal definition. For two bundles, suppose the consumer weakly prefers x1 to x2, but does not weakly prefer x2 to x1, right? If both these statements are true, then we can say that x1 is strictly preferred to x2, right? So that's the strict preference relation. That will be this strict inequality kind of sign. Indifference can also be defined in terms of the weak preference ordering, and that definition is here. So for two bundles, if it's true that x1 is weakly preferred to x2 as well as x2 is weakly preferred to x1, then we will say that the consumer is indifferent between these two bundles, right? So these two slightly different notions are defined in terms of the weak preference ordering. some of the properties, some of the assumptions we make about the weak preference ordering will have implications for these preference orderings too. And in the problem set that I will give out on this topic, you will be asked questions of that sort. That, for example, if the weak preference ordering is transitive, can we deduce that the strict preference ordering will also be transitive, or that the indifference relationship will also be transitive, right? So those will be logical conclusions which you can prove in a watertight way, and I'll give you some exercises of that sort. Okay, so let me get to the list of axioms. There will be 4 axioms, and we'll later bring in a 5th one. And these 4 axioms will have powerful implications. Yeah, and they'll really sort of build up a nice theory of choice. Axiom 1, we can call it the completeness axiom. So here's the formal definition. You know, the formal definitions often look a little terse, a little maybe slightly intimidating, but what they mean is quite simple. Keep an eye out for logical quantifiers, meaning that, you know, the statement here starts with for all x1, x2, okay? So any 2 points that you pluck out from that space, any 2 consumer bundles you take, the completeness axiom says that at least one of these statements can be made. If you ask the consumer will be able to give a definitive response about how she ranks x1 and x2. She will be able to say either that x1 is weakly preferred to x2, or that x2 is weakly preferred to x1. And she might say both, actually, in which case that will mean that she's indifferent between these 2 bundles, right? Both is allowed. But what the completeness axiom is ruling out is the consumer being not knowing her own mind. That the consumer says, I don't know how which I like better. So that sort of dithering, that sort of indecisiveness is what is being ruled out by the completeness axiom. Yes? Now, if you ask, is this a good axiom to make? Is this a good assumption to make? We can think of situations in real life where, we are confused. Maybe you got into ISI and Delhi school, into both the master's program, and maybe you were, for a while, you didn't know which to choose, and you agonized over the decision. And then you chose to come to Delhi school. Excellent, good choice. But we can all think of, even trivial choices, like you walk into the canteen or the restaurant and you're kind of dithering over what to eat. Now, but much of the time, also introspection will tell us that we have a fair idea of what we want. A. And secondly, if you don't make the completeness axiom, it's hopeless to build a theory, right? If you're not prepared to assume that the consumer knows what she wants, then how are we going to predict her behavior, her choices? Yes. So it's almost imperative that to build any kind of predictive theory of choice, we have to make an assumption like completeness. Yes. So this shouldn't be too controversial. So let me move on to axiom 2, and there we'll pause a little longer, and I'll solicit your opinions or reactions.
Sir?
Yes.
So
Yes.
are we saying that in axiom 1, we are saying that the consumer is rational, like indirectly?
Let us, be a little cautious about using the word rational. The word rational, in my opinion, is too broad, right? If you say somebody is being irrational, there can be too many senses in which you might say so. Okay. There's one thing which I pointed out in an earlier lecture, right? In everyday use, sometimes we say irrational when people exhibit preferences which we think are not good for them in the long run. For example, somebody's eating junk food, yes, and you say, oh, you're being irrational because you'll clog your arteries and you'll start having high blood pressure or cholesterol, and you'll suffer the consequences. Your food habits and preferences are irrational. The sense in economics and choice theory and decision theory, we don't include such a sense of rationality, right? In that case, we might say, oh, your preference and your choices are harmful to your health. We might say that, but we won't say irrational. Basically, there's you're trading off the temporary kick from eating your pakoras, right, and the possible future health consequences that you might suffer. Uh, so if somebody has preference with a low discount factor, for example, that I care much more about the current pleasures than about consequences 5 or 10 years down the line, in one usage we won't call it irrational. Yes. Okay, so having eliminated that, as we are discussing theories of this sort, again, departures from the standard model can happen in multiple ways. This axiom may be violated by one person, that axiom may be violated. So at this point, we don't want to sort of fling around the term irrational willy-nilly, right? That any departure from this framework will call irrational. That's just a semantic point. That's a matter of language. I don't want to use that. If the completeness axiom fails for an individual, let's just say that there's no way we can predict her choices. If she doesn't have a ranking, God knows how she will choose. Maybe she'll toss a coin, who knows? Well, actually, that may not, there are models of choice, the so-called random utility models, where some amount of randomness is built in, that sometimes the agent sort of tosses a coin, maybe. So even that could be sort of built. But as a starting point, we don't want to drop the completeness axiom. What we want to call somebody who violates the completeness axiom, that's somebody whose preferences are incomplete. Let's keep it in that sort of technical language.
So, what do we mean by this phrase, preference loops or cycles?
Coming to it. So that's transitivity. I'll tell you.
Oh,
So the second assumption is going to be transitivity. So take any three vectors of consumption bundles. If x1 is weakly preferred to x2 and x2 is weakly preferred to x3, is it always the case that x1 is weakly preferred to x3? Suppose it is always the case. Suppose for any three bundles you pick out, this statement can be made, right? Then the preferences satisfy transitivity. Okay. Now, what if transitivity was violated? Yes. So I go to the canteen and there's a pizza and there's dosa and there's a sandwich. Okay. So suppose I prefer the pizza to the dosa to the sandwich, and the sandwich to the pizza, right? What did I say first? So pizza is preferred to dosa is preferred to sandwich is preferred to pizza, right? So then we have a preference loop. So whichever of the three items I order, immediately I'll find something on the menu which I like better. So immediately I would want to switch to something else. But this is a never-ending process. I'll go around like a dog chasing its tail, right? So whatever item I select, I have reason to move to another item because there's something better on the list. So in that case, again, it would be close to impossible to develop a theory of choice. Unless you bring in, sort of coin tossing and stuff like that. So that is what the transitivity axiom is ruling out. that the consumer we are going to study, whose behavior we are going to theorize on, doesn't have these preference loops or cycles, right? In other words, the consumer has a ranking, a list. There's a favorite item, there's a second favorite item, there's a third favorite item, and so it goes. So there's a quasi-ordering because some items may be ranked equally. Okay, so it's possible that I say that A is my favorite, B is my second favorite, C and D are both my third favorites, followed by E. Yes. Now, is this a reasonable assumption?
So can we claim like that transitivity implies completeness, but the converse may not be true?
No. Transitivity um, um, does not imply completeness. Okay, so we can have somebody who has transitive but incomplete preferences. What does transitivity say? That if the consumer is able to rank X1 and X2 in this way, and X2 is with X3 in this way, if, okay, then this has to be true. So I can think of a consumer who, there are four choices, A, B, C, and D. And A, B, C are well ordered, right? Between those three, the consumer says, I like A the best, B next, C is the third. But I don't know how I feel about D. It's one can imagine a consumer who has a mind like that. Yes. I can rank a subset of the alternatives I face in a transitive manner, but there are other elements in my choice set which I'm just ambivalent about. I don't know whether I like them better than these three or not. Yeah.
Okay, so got it. Thank you.
In general, when we are building up an axiomatic theory, we don't want to do two things. We don't want to bring in axioms which contradict each other. That if axiom 1 is true, axiom 2 cannot be true. We don't want that clash because then we have a logically inconsistent system. We also don't want superfluous axioms. Yes, meaning that I write down axioms 1, 2, and 3, and it turns out that axiom 3 is actually a logical consequence of axioms 1 and 2. If that is the case, then it's less serious than the first case, but I look a little silly, right? I have not been economical. I have imported axioms into my analysis, which should really be theorems. Right? I should have written down axioms 1 and 2, and then instead of calling axiom 3, I should have called it theorem 1. Right? I should have been able
Excuse me, sir. Excuse me, sir.
Yes, Tanvi.
Sir, in axiom 1, completeness, both of these inequalities can hold. Like, shouldn't it be not both? Because if we are having both of these, doesn't it lead to confusion?
No, it doesn't lead to confusion. It leads to indifference, right? So indifference is something that we understand and which we would like to accommodate in our theory, right? It is not outlandish for me to say that, between a can of Pepsi and a can of Coke, I really don't care, right? Each is as good or as bad. So many consumers in many situations will just shrug and say, oh, between these two choices, what do I care? Either is fine. So that is indifference. And if both of these statements are true, that basically means indifference. That's not confusion. I'm not ranking either above the other.
Okay, sir.
Yeah. But I'm not saying that I can't tell, that I don't know, or I am confused. I'm not saying that. I'm just saying they're equally good.
Sir,
Yes.
just one question. Sir, when it comes to transitivity,
Right.
can it be possible that we sort of rank our consumption bundles on different characteristics and thus transitivity may not hold? So for example, like the example that you took where pizza was preferred over dosa, and then dosa was preferred over the sandwich, and then so the pizza is preferred over the sandwich. Maybe when we compare dosa and sandwiches, maybe we like the crispiness of the dosa. And
Right.
when we compare the pizza and the dosa, maybe we like the cheese of the pizza.
Sure.
But then when we compare pizza and sandwich, then it might be, there's some other characteristic of the sandwich that we like much better than the pizza,
Yeah.
and thus transitivity may not hold.
Yes.
So
Okay.
that's possible, right?
No, absolutely. So whenever we are shopping, we are you're looking to buy a new computer. There are several things that you care about: the processor speed versus the weight of the machine. The screen quality. So you're looking at different dimensions, and when you're comparing two models, often you have to handle this, that one model looks better to you in terms of its screen. It has a brighter, sharper screen, but the other model seems to be faster, right? It has a better processor, more memory, or something like that. But as consumers, eventually we get down to making a comprehensive assessment, right? We take these multiple dimensions, multiple qualities, and we somehow have to add it up and say, okay, all things considered, do I like this Dell Inspiron or that Sony Vaio model, right? We have to make those decisions all the time. Yeah. Sometimes processing in our minds and coming to it, it takes time. In that interim period, we are not satisfying the completeness axiom, but as consumers, we are doing it all the time. That okay, this one is tastier, but the other one is healthier. This one is lighter, but the other one is faster. So how do I sort of holistically rank this model versus that model? Yeah. If I fail to do so, then I failed the completeness axiom. That's what it takes in these cases when there's multiple dimensions and multiple characteristics. That's what it takes for a consumer to come to a conclusion about which she likes better, right? So if she cannot do it, her preferences are incomplete, and we as analysts studying her will also stumble, and we'll be finding it hard to predict her behavior.
Oh, all right, sir.
Okay, let me just make a little digression here to give you a sense that transitivity is not such a trivial assumption to make. Yeah. And I don't know if you have seen this before, maybe not. You guys have seen the paradox of voting in your undergraduate?
Yes, sir.
Yes,
Yes,
sir.
sir.
So what is the paradox of voting? Somebody can summarize it quickly? So actually not the paradox of voting, I meant to say the Condorcet paradox.
So it's rank-based ordering, like utility ordering.
Did you study any social choice in undergraduate?
Yes, sir.
Arrow's
Yes,
impossibility
sir.
theorem and all that?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So,
Yes, sir.
yeah, so I won't spend too much time, but think about that, right? So there's this so-called Condorcet paradox. The story is that there are three roommates, let's say, who have a common TV. They live in a dorm, hostel. And in the evening, they want to watch TV for an hour. And there are three channels, one showing the news, another showing sports, and the third showing um, a film, a movie. Now, each of them may have a very definite ranking. So, for example, roommate one may have the following ranking. News, preferred to sports, preferred to movie. The second roommate may have, again, a clear ranking, but a different ranking. Yes, the third may have yet another ranking. Now, since there's one TV, they have to agree to some choice of channel. Now, one way they can do it is by creating a social preference ordering out of the individual preference orderings, right? They could say, okay, here's a process. We will create a social ordering following this process. Now, one of the sort of ways in which you may want to aggregate in these orderings. Actually, let me show you very quickly how this works. I don't know how this. Anyway, let me write here. So let's say the so individual one thinks that news is strictly preferred to sports, it's strictly preferred to the movie, right? For person two, S is preferred to M, is preferred to news. And for three, it's M is movies is the favorite, followed by news, followed by sports. Suppose these are individual preference orderings, right? And suppose we decide to aggregate this into a social preference ordering by using pairwise majority voting, meaning that first there will be a majority vote over news and sports, then between sports and movies, and finally between movies and news, right? And in each such bilateral contest, whichever option gets the majority, the majority vote is put higher in the social ordering. Yeah. So if there's a vote between news and sports, notice that the first person prefers news, and so does the third person. So news will get 2 votes when it's fighting against sports. So socially, news is ranked above sports. Then when we compare or vote between sports and movies, again, 2 people prefer sports to movies, right? So that'll win. And finally, if you're voting between news and movies, note that 2 people, individuals 2 and 3, rank movies above news. So that'll win. So what do we have now? If you look at this, does this satisfy transitivity?
No, sir.
No,
It doesn't.
sir.
So we have a cycle, a loop. S and M. Yes. So that's a tricky situation. What sounds reasonable, that let's have pairwise votes, leads to blind alley. Through pairwise voting, whatever alternative is selected, there's always some other alternative which a majority will prefer. So the point is that transitivity can get easily violated in situations where the choice is made by a collective, by a group of people, rather than a single person, right? Notice that each person satisfies transitivity, but the group, when group preference is defined in this particular way, pairwise majority voting, the group does not satisfy transitivity. So transitivity is an assumption which is not to be taken lightly. We have to be sort of at the back of our minds. We have to make a note that in certain contexts, transitivity may fail. But for now, we will stick with it, right? At the individual level, it doesn't seem too bad of an assumption. Okay. The third assumption is somewhat technical. So it's the assumption of continuity. Essentially, this assumption makes sure that ultimately when we develop the idea of an utility function in this framework, I'm putting it in scare quotes because it will be a very different notion of utility. But when that comes up, the so-called utility function will end up being a continuous function so that we can apply in all the tools of calculus and everything to that function. So that's what this guarantees, technically speaking. But it also has some appeal to our intuition. The spirit of the assumption is that bundles which are very similar are also evaluated very closely. So a consumer, if two bundles are almost identical, if they differ only slightly in some detail about how much quantity of each good is there, then the consumer may rank one over the other, but they're ranked pretty close in some sense. Okay, that's the sort of gist of the continuity axiom. Let me now state it technically for you, right? And then we can discuss what it means. There are many ways in which the continuity axiom can be stated, okay? And this is one way. So let me use a little picture to explain what all this is saying. So let me draw a picture. It's always useful to discuss these concepts in the case of two commodities, right? But the ideas are much more general. So let's say there are two goods, X1 and X2 are their amounts. What the continuity axiom is saying is the following. Let's take two sequence of points, right? The first sequence is the X n sequence, right? So let's say X1, notice that it's a superscript. So we're talking of vectors here. X2, etc. And this sequence converges to some X, meaning that the points are getting closer and closer. As you move further along the sequence, the point is arbitrarily close to X. So X is the limit point of this sequence, right? The whole sequence is converging to the point of X in the usual sense of convergence. Now, there's another sequence somewhere in this space, and that's the YN sequence. So that's another sequence of consumption bundles, Y1, Y2, and that is converging towards some point X. So Y and X are the limit points of these two sequences, yes? And suppose the sequences have the property that all along the sequence, Xi, the ith element of the first sequence, is weakly preferred to the ith element of the other sequence. Okay. So X, in this sense, is the better sequence of choices, yes, compared to Y. Every element of X in the X sequence is better than the corresponding element in the Y sequence. Okay. Now suppose we look at the limit point, and suppose this is at the limit, the ordering is flipped, it's reversed, suppose, right? So in the limit, we find that Y, the limit of the Y sequence is somehow preferred to the limit of the X sequence. This is what our axiom is ruling out. Our axiom is saying, no, our consumer who we are studying will not display this. This is ruled out. All along the sequence, if X is preferred weakly, then at the limit, X will continue to be preferred. All right? So that sounds a little convoluted, and I'll try to make it a little clearer. So that's one definition. Another possible definition is the following. Um, so let's choose a point X. Let's call it X0. Okay. I can define a set of points, call it well, something like X0. Well, it should so what is this? This is a set. Right? What is this set? It's a set of points in this space which are at least as good as X0. So it's a weakly better set. Yes. So I take any point in this set, I will be able to write that that point is weakly preferred to X0. Right. And if I collect together all those points, I have a set. Something like this. So an alternative definition of the continuity axiom is that this set is a closed set. Closed set means it contains its boundary points. Okay. It's not an open set. It's a closed set. And similarly, another set we can define is this. This is the set of points which have the property that X0 is preferred to each of them. Right? So this is the weakly better set, this is the weakly worse set. So another way to state the continuity axiom is to say these two sets will be closed sets. They will contain their boundary points. The boundary points will not be outside the set. It turns out that these two definitions are logically equivalent. One implies the other. Right? So whichever way you want to state it or understand it is equally valid. I'm not going to give you that proof. You can try to prove that yourself. I'll leave that to you. But this is how the textbook defines the continuity axiom. So I'll stick with that definition. Once again, the intuitive meaning is that, you know, for small changes, the consumer's attitude towards a consumption bundle doesn't radically shift. Yes, that's the sense in which, you know, you take a basket of goods and you add a grain of sugar to one and remove one tea leaf from the other. It's not that the consumer thinks of it in a vastly different way. That's the meaning. Questions?
Sir, in the diagram that you made, the two sequence xn and yn.
Yeah.
So each element of x and r means x1, x2, and each element contains both the goods like x1 and x2, right?
That's right. So when I put superscripts, I'm talking of the vector. When I put subscripts, I'm talking of the quantity of that particular good.
And similarly, the element y1 of sequence yn contains both goods x1 and x2.
That's right. That's right.
Okay, thank you.
Yeah. Last axiom.
So in the previous.
Yeah. Go ahead.
Sir. So in the previous question.
Right.
Will the social preference will exist or not if transitivity has failed?
Okay, so in that example, the social preference, well, you can say it in various ways. First of all, in that example, we were trying to construct social preferences in a particular way, namely pairwise majority voting, right? You can think of other ways to try and construct it. But having said that, let's stick with that. Now, through pairwise majority voting, essentially, transitive social preferences do not exist. Again, it becomes a somewhat semantic issue. Do you want to say social preferences don't exist, or do you want to say they exist, but they are not transitive? Well, I mean, you know, in any case, it's a problem because intransitive preferences give rise to, you know, choice becomes impossible. So social choice then will become impossible. So, you know, people may want to put it in various ways. Let's just say that using that method of aggregation leads to a breakdown of transitivity, which means things are pretty bad, right? Now you could say that, well, we may want to try to aggregate these individual preferences, which are well defined, well behaved, they're transitive and everything. We can try to aggregate them in somewhat different ways. There are other ways, there's something called border ranking, for example. So you can use other methods. The more generalized form of that example is Arrow's impossibility theorem, which will be discussed in its full glory by Ram in the second part. You have probably seen some glimpse of it in your undergraduate. But Arrow's impossibility theorem essentially, put very loosely, says that in that example, the problem we ran into when we tried to apply pairwise majority voting, whichever method of aggregation we choose, as long as it satisfies certain minimal properties that we wanted to satisfy, whichever method of aggregation we choose will run into the same problem. So the problem is much more general. It's not just restricted to pairwise majority voting.
Sir?
Yes.
Sir, in axiom 3, I think I missed the point where you said that I really couldn't get the second point, like bundles which are closed in quantities are closed in preference. I mean, what does that mean? What does closed in preference mean?
So look at the example, right? Suppose continuity is violated. Suppose this is true, right? That all along the sequence, the X bundle is preferred to the Y bundle, but in the limit, it's not. Let's say that is the case. So that means when you compare Y and X, Y is the favorite. Okay. But I can find two bundles, one very, very close to Y, meaning it's almost the same as Y, but only some quantities are slightly different. And I can find another bundle very, very close to X, where the favorite bundle is this one. Okay, so by slightly changing, although I prefer Y to X, I can make slight changes and reverse that reference, right? That is being ruled out. So,
sir, I got it intuitively, but what does, like mathematically, what is closed in preference means?
Close means that close, first of all, close as a bundle being close means that the quantities are almost the same, right? Of the different things. In Euclidean space, it's within a small epsilon ball of the bundle. That's what means being close. Being close in preference means that, well, if that language is confusing, forget about it, right? But this is saying that if I like one thing better than the other, and you make the slightest, smallest adjustments to what they contain, I suddenly won't change my mind. Okay, that's a spirit.
Okay, sir.
Yeah.
Okay, sir. Thank you.
Yes.
I have a small question.
Yes, Divya.
I don't understand how the continuity axiom is equivalent to us getting that each of the preference relations gives us a closed set.
Okay, so that's what I said. I'm not going to do the proof of that, so I'll leave that to you as an exercise. Try to prove it, and we can discuss it later. I'm just stating the fact, and some of these things I'll leave it to you to. It's a bit of a challenge for you to try and work it out. So okay. If you cannot, then let me know.
Sir.
Yeah.
Sir, could you please give us an example of any real example of a sequence of bundle of goods, because I'm not able to connect it with the concept of limit point in any real example.
Well, first of all, okay, the mathematical notion is, okay, forget about the mathematical notion. I mean, what does it mean to say a sequence of points or one point being close to another? So you start with a consumption bundle, right? It has a certain amount of sugar, a certain amount of flour, a certain amount of rice, and a certain amount of tea, and so on. Okay, and you have another consumption bundle which has those same commodities in different amounts. And now what you're doing is you are um, uh, changing the amounts in each of them. Okay, you're taking out a spoonful of sugar first from one bundle, and let's say a spoonful of flour from the other. And so you're making small changes in quantities. That's what it means, right? The course, what what we are putting down here in maths and pictures. If you, what does it mean? It means that you're making these little adjustments to your two initial bundles, and you're making a sequence of such adjustments. Eventually, you're reaching two new bundles, right? First, you took out a spoonful of sugar, then half a spoonful of sugar, then a quarter of a spoonful of sugar, and so on. So you make some little adjustments which become vanishingly small. Now that's not hard to understand, right? That is well defined. I mean, that's not pure mathematics. I'm translating it into you know uh, what's going on in real terms, right? So this is saying that you start in the grocery store. They have put two bundle of things next to you, bundle A, bundle B, and you tell them that I like A better than B. You look at into the contents, you say I like A better than B, and they start using their spoons. They're adjusting their amounts, and their adjustments are getting smaller and smaller. So you liked A better than B, then they took out a spoonful of flour from one and a spoonful of sugar from the other, and they ask you the same question, which do you like? And you still say, I like A better than B, right? One is on the left, one other is on the right. So as they're doing these adjustments and making the adjustments smaller and smaller, all along the way, you're saying, oh, the one on the right, on the left, that's what I prefer. That's what I would take home if you give me the choice. And then in the end, when they have just taken out a grain of sugar from here and a smidgen of flour from there, suddenly you change your mind. That is what is not allowed. Yes, that's what it means. And that's the best I can do in translating the mathematical definition to some, commonsensical description. Okay, so let's move on. I will be happy to, clarify later, but let's, the last assumption is strict monotonicity. I want to get to the result quickly. So this is pretty simple. This is saying that, if you add certain quantity of, if you increase the quantity of one good without decreasing the quantity of any other good, then the new bundle should be preferred by the consumer to the old bundle. More the merrier, right? That's the last assumption. Now, let me get to the main result. What's the benefit from assuming these things? So the benefit is the following. If these four axioms are satisfied, then there exists a continuous increasing function which represents these preferences, right? So then we can, in principle, write down a function, and it will be a continuous function, which represents the preferences in the following sense, that if one bundle is preferred to another, the function will always spit out a larger number corresponding to the more preferred bundle. So if X1 is truly preferred by the consumer to X2, then this function that we can construct, that is the claim, will always attach a higher value to X1 instead of X2. Okay? So we can call this a utility function. We can call this a preference representation function. Its exact value does not matter. What matters, the information that it captures is the ordering or the ranking, right? Higher values will successfully represent more preferred bundles. Now, suppose there was a finite number of alternatives, 10 alternatives, yes? And the consumer indeed had a transitive, well-defined preference ordering, right? So there was a favorite, there was a second favorite, there was a third favorite, etc. In that case, this theorem would be trivial, okay? The most preferred bundle, I can give it a score of 10 and say, this is the one I like most. The second most preferred bundle, I can give it a score of 9, right? So that the numbers, the value of the number will represent which I like better. Now, I could have given different numbers, right? Instead of 10, 9, 8 as the quote unquote utility numbers, I could have said, okay, my favorite, I give it a score of 100. My second favorite, I give it a score of 90, and so on. Okay? Any number which successfully captures the sequence would do the job of successfully sort of portraying what the relative ranking of the various items are in the consumer's mind. So the reason that this is non-trivial is that we have an infinite dimensional commodity space, right? So it's not immediately obvious that we will be able to find functions like this which represent the consumer's preferences. So that's why the theorem is useful and non-trivial, that we have to sort of spend some effort in proving it. Now, I'll talk about the proof, and that will be tomorrow's lecture because I'm, again, too short on time. But let me skip to the next result and I'll discuss the reasoning and the proofs a little bit. But today, let me state them and talk a little bit about their significance. Now, you might ask that, okay, if those 4 axioms are true, then yes, we can construct a utility function. Is it unique? Is there only one function will do the job? Yes. And the answer to that is absolutely no. The answer is that, if I can create one utility function, I can always construct many other utility functions which capture the same preferences, right? They have the property that they always give higher numbers to more preferred bundles. For example, if I start with a utility function, and if I just create a new function by multiplying that utility function by 10, right? So I have a utility function u of x. I create a new function which is 10 times u of x, right? So every utility number gets multiplied by 10. Obviously, that also captures the same preferences, right? In the finite case with 10 alternatives, I could give them numbers 10, 9, 8, and so on. I could have also given them numbers 100, 90, 80, and so on, right? That's exactly what I did. I multiplied each number by 10, but their relative values remain the same, yes? So utility functions in this ordinal framework are not unique. And the other result is that any monotonic transformation of a valid utility function gives you another valid utility function. So if I have a valid utility function u of x, which captures preferences, and if I put it into another function f, whose derivative is non-negative, whose derivative is strictly positive, right? For example, I take the log of the u function, right? Or I multiply it by a constant, or I add a constant to it. All of those are monotonic, positive monotonic transform. So every positive monotonic transformation gives me another valid utility function. Okay? Now, I'll prove both of these. Now, what is the usefulness of this? Why are we going through these, jumping through these hoops? The thing is, when we study the consumer's problem, studying it using rankings is very hard, mathematically, analytically, okay? When we are maximizing a function, there are lots of mathematical tricks that we can use to analyze that problem and draw conclusions. So conceptually, we didn't want to start with an utility function because it sounds like a kind of a nebulous concept. It's not like height or weight. It's not concrete. It's not measurable. That's why we didn't want to start with it. But having thrown away utility functions, we were really missing it. That once we start analyzing the consumer's behavior, try to build up a theory, we really wanted something like functions, so we use calculus, we can use maximization techniques. So that's where all of this comes in. conceptually, we start on solid ground, rankings, because they are well-defined, they're understandable. And then we are saying that if the rankings are well-behaved, if they satisfy certain properties which have some intuitive appeal, then we can act as if there's a utility function in the continuous loop. Guys, switch off your microphones, please. Right? Now, you see it a lot in the physical sciences. For example, you know, in classical optics, right? Studying the behavior of light, there are things like laws of reflection, laws of refraction. You know, we may have studied it in school and so on. There's a principle called Huygens principle, which says that in going from point A to point B, light always follows the quickest path, right? And if you take that as an axiom, as a principle, you can derive all kinds of laws of reflection, refraction, etc. So it is as if light is in a hurry. It is as if light wants to go from A to B without wasting any time. Now, nobody seriously believes that literally, that light is not a person who has objectives. It's just that light's behavior can be, the properties of light in the physical world can be understood by postulating this sort of maximizing behavior of particle light. So that's what we're doing in consumer theory. In the real world consumer, we don't literally mean that if you go and ask people on the street, what is your utility function, they'll look at you like you're mad, right? That's possible. It's just that our theory says that if people can rank in a certain way, then it's as if they're maximizing some utility function, as if, right? Not literally so, but in an as if sense. Okay, questions?
So we have a class right now.
Okay, so I will end. So in tomorrow's lecture, we will look at the proofs and then we'll take it forward from there. And so if you have questions, let's have a discussion at the beginning of the video after that. Okay. Okay, guys. I'll stop the lecture now.